In this video, we're going to talk for a bit about disk organization, how the operating system interacts with disks. We're going to talk about disk partitioning, and we're going to spend most of our time talking about RAID and looking at some specific examples from specific machines. Okay, so I'm looking at the desktop. I'm actually looking at the right screen of a two-monitor Windows display, and I've put my computer up here in the upper left-hand corner. If I right-click on my computer, or just computer, and choose the option called Manage, which you may or may not be able to see depending on whether you're logged in with administrative privileges, on a Windows 7 machine, Vista as well, I believe, you'll see a screen like this. And you'll notice there's three main categories: System, Tools, Storage, and Service Applications. If you open System Storage, you'll see this Disk Management category. And click on that, and chances are you'll see a display something like this. Okay. Now, I'm going to spend a little time here, and then I'm going to go to a few other screen captures, and then we'll come back. Okay, what this is showing me is that I have a series of at least what Windows thinks are disk drives attached to this system. This first one here, disk 0, is a 298.02 gigabyte physical disk, okay? Or at least Windows thinks it's that, and it's online, so Windows is actively using it. Then disk 1 through disk 4 are actually not disks at all. What they really are is the workstation that I'm recording this video on has a memory card reader that can read multiple formats. There are 4 slots in there for various size memory cards, and basically each of these is a corresponds to one of those slots. So although they're not really disk drives, they appear to the operating system as disk drives. And when you put a card in there and start reading it, essentially the operating system is interacting with it using exactly the same service layer calls and exactly the same mechanisms as it would with an ordinary disk drive. And the disk driver is taking care of whatever translation is necessary. Okay, down here towards the bottom, you see I have 3 devices labeled as CD-ROMs. One of these is actually a virtual device, this one at the bottom called CD-ROM 2, so I'll ignore that for the moment. The other 2 are in fact actual disk devices. So CD-ROM 0 is in fact an actual CD-ROM or CDRW read-write device. Okay, has no media currently stored in it. And it's been assigned to drive letter D. Okay, the second device, CD-ROM 1, is actually a DVD drive. I believe it's actually a DVD plus minus RW. I don't remember if it does dual layer or not. And it has been assigned drive letter E, and it has no media in it. Okay, but let's go back for a minute and focus on this actual thing that is actually a disk drive, or at least looks to the operating system like a disk drive. So this is a disk that looks to be just a hair under 300 gigabytes, and the graphic image here to the right shows me that this disk is actually broken up into 3 pieces for purposes of storage management. Okay, and this is actually fairly typical for a laptop or a desktop computer disk. The first partition here on the left is labeled 118 megabytes healthy OEM partition. Okay, and basically what that is, most PC and laptop manufacturers today, when they format a disk, they have some custom manufacturer-specific programs for things like backup and recovery, or for running diagnostics that are specific to the manufacturer. And what they do is they take a small portion of the disk and they create a partition on it. A partition is one, or a volume if you like, to use the language of the textbook chapter you read. And on there they store data and programs needed for those diagnostics, for whatever those utility programs are. Okay, so the operating system sees that this partition exists, but it's basically ignoring it because it's not something that's formatted and intended for use by the operating system. What the operating system is using is this second partition here, which occupies nearly the entire disk. It is formatted in a format called NTFS, okay, NT file system, where NT is from Windows NT, which predates Windows 7 by a few versions. And I see that this disk has quite a few things that describe it. I've got system, so it's a system disk. We boot from it. It contains the page file for virtual memory management. It is active. If there's a dump file generated as a result of system crash, this is where it's stored. And it's also the primary partition, which means it's the one that will boot by default if there are multiple boot partitions. And I see this has been assigned the drive letter C. Okay, so this partition in hard disk drive parlance is in fact a single volume in file management or operating system parlance, which has been assigned the Windows drive letter C:, and is actively managed as a single unit. It is a single unit for purposes of security, backup and recovery. It has a single storage allocation table. So on, it's a single hierarchical directory structure, so on and so forth. Okay, this last one here, note it's pretty small, 13 megabytes. That's not a lot by modern standards. It says unallocated. What happens with these main partitions is they have to be an even multiple of the allocation unit size, and there's actually some other restrictions on how they're set up. And often what's left over is simply, after you do an integer divide by whatever of the available space by whatever that minimum unit size is, you've got a remainder, and this little tiny partition at the end is the remainder. Okay, so in summary, Windows, at least this Windows on this particular computer, thinks that there is a single hard disk drive on the system, and it sees inside that hard disk a small OEM partition, a large partition that it's managing as the C drive or the boot drive, and a much smaller leftover partition that's basically too small for it or anything else to be useful. Let's see, any other information up here? Well, if I look up at the top part of the display, I see this is a basic disk in Windows parlance, and we don't need to get into basic versus dynamic. I see that it has 40 gigabytes or almost 41 gigabytes of free space, and that represents 14%. I also see that there's no fault tolerance turned on. It's not mirrored, it's not RAIDed or any other sort of thing. And because there's no sort of RAID associated with it, there's no overhead associated with it. Basically, all of the space is available for use. Okay. Now, to contrast this, I want to look at a couple of similar screen captures from much older computers that I have stored in my archives. And let me put this one up towards the top here, and let's go grab one of these older ones. Let's see, I'll go grab this one. Okay. This one is definitely from an older computer. Okay. I don't remember when I actually captured this thing. I'd have to go back and look at the date on the file. Well, I paused temporarily and I went and looked at the date on the file, and it says January of 2009, but I suspect I'd made a copy of it and possibly cleaned it up or something, because I'm pretty sure this goes back quite a few years before that. All right, so looking at this particular disk management output, note that although this is from an earlier version of Windows, probably let's see, what would it be in this generation? Maybe Windows NT4 or possibly one version later. I see that the nature of the display is really not all that much different from the modern Windows 7 version. Okay, looking at this display, I see there is a disk 0, which is at just a hair over 19 gigabytes, a pretty healthy sized disk at the time. Okay, and then there's a CD-ROM, and there's actually a removable drive. Well, there's a good indication of how old this thing. There's something called a ZIP 250, and if you don't know what a ZIP 250 is, that's because it's an antique. But I see that this disk drive has been broken up into three pieces, three partitions. One of about 4 gigabytes, one of about 10 gigabytes, and another of about 5 gigabytes. They have been assigned the drive letters C, D, and E. So this is an example of one disk, physical disk, being broken up into three separate volumes, where each volume is in fact managed by the operating system. Each volume, as a Windows volume, has been assigned a drive letter, C, D, and E. Now you might say, well, why would anybody have done this? Why didn't they just make the whole thing a C drive? Well, it probably had to do with backup and recovery. My guess would be that the C drive here, well, I don't have to guess, I can tell it's healthy system drive. So it was the boot drive. It had the operating system, and yes, back then the entire operating system could fit into roughly 4 gigabytes of storage with a bit left over. And if I wanted to back up just the operating system, I could back up this entire C drive. And if I then needed to recover, I could recover this C drive. Since it was just a hair under 4 gigabytes, that roughly corresponds to the capacity of a single backup tape of that era. Okay. Whereas this program disk, well, it's bigger. It would take multiple tapes, but it probably doesn't need to be backed up all that often. You could always just, if say the whole disk drive died, you could put in a fresh disk drive. You could recover the operating system from the backup of this C drive. At that point, you'd be able to boot the system. You could then partition the remainder of the disk into D and E. If you had backups for them, you could recover them. But in the case of D, if you didn't have backup, well, you could always just reinstall all the programs that were on it. You know, whatever, Microsoft Office or Adobe Acrobat or whatever else might have been installed on this thing. Okay, so this is an example of a single drive being managed as 3 separate volumes, 3 distinct pieces. Each of those volumes with its own storage allocation table, its own directory structure, its own set of security measures, and each volume can be backed up and recovered as an individual unit independently of the other 2. But of course, since all 3 volumes reside on the same physical disk, if disk 0 here takes a head crash or suffers any other sort of fatal hardware problem, all 3 volumes are lost. Okay. Now let's take a look at another old but slightly more complicated. Let's see. I'll just minimize it. Okay. Here's another oldie but a goodie. Okay. Okay, this one has the same date actually on the file, but my guess is once again this is considerably older. Note here I have 2 physical disk drives. Okay, disk 0 and disk 1, and they're both 16.95 gigabytes. Okay. These are actually fairly old SCSI disks. I'm pretty sure they were SCSI. Okay, and they're twins. They are same manufacturer, same model. You know, probably consecutive serial numbers or something pretty close to that. Now let's take a moment and look at the breakup of this first one. Okay, this first one is broken into 3 partitions of roughly 4 gigabytes, 16 megabytes, and almost 13 gigabytes. And the first 4 gig partition is a C partition. Once again, this is probably the boot disk. The operating system's installed on there. The second one, 16 megabytes, I'm not sure what that was. That may have been a diagnostics partition, or maybe it was just, you know, extra space that couldn't be used. And then this last partition on here is labeled data disk, so we know that's what was used to store data on this machine. But note the color coding here. The C drive is shown with a red stripe at top, and if I look down here it says mirrored volume. And if I go to disk 1, I see there's another partition on disk 1, also labeled C, of exactly the same size. Okay. And if I come up to the textual description of above, I see this volume C's layout is a mirror. Okay, so that's, you know, that's a RAID, is that a RAID 1 or 0? I never remember which. I think it's a RAID 0. It's a NTFS file system stored on it. It has 4 gigabytes of capacity, okay, and this one's got almost half that capacity free. So even though I have 4 gigs from disk 0 and another 4 gigs from disk 1, that does not add up to 8 gigs because I have, in this case, a mirror. So this is, in fact, a mirror, okay, and therefore the effective capacity is half of the allocated physical space. 8 gigabytes of physical space are allocated, 4 on this disk, 4 on this disk, but essentially they're duplicates of one another, so effectively only 4 gigabytes of storage is available. Okay. In contrast, let's look at this last partition labeled D, which is shown to all the way to the right for disk 0 and all the way to the left for disk 1. It's color coded in kind of this teal, teal green, and that's called a striped volume. Okay. So data disk D is a striped volume, okay, and its capacity is almost 26 gigabytes, which is the sum of these two. Okay, so in this particular layout, disk C is mirrored for improved fault tolerance. So if disk 0 or disk 1 dies, I can still boot the machine because both of these have a valid copy of the boot partition C. On the other hand, the volume D, or D colon, is split across the two disks in a striped fashion, such that data is stored half on this disk, half on this disk, and if one of these two disks goes down, D is gone, or at least half the data on it is gone. So I have fault tolerance here on C, but I don't have fault tolerance on D. The fault tolerance on C is costing me storage space, namely 4 gigabytes. The lack of fault tolerance on D is allowing me to extend the storage capability across partitions available on both disks. Okay, and assuming we're doing regular backups of D, this sort of approach actually would have been fairly typical of, say, a low end to mid-range server of, say, the mid-2000s, where I have a mirroring on C so that if a disk died, I can reboot. Okay, so presumably, say disk 1 died. Disk 1 just goes away. Okay, what happens on this machine? I take it down, I put in a new disk in place of disk 1. Okay, I boot off of disk 0, C. Okay, I then repartition disk 1 with these same partitions to match the other ones. First thing I'll do is reestablish the mirror on C, so basically all the data currently stored on C on disk 0 will get copied to the mirror partition on disk 1. At that point, the fault tolerance will have been reestablished. Okay. Second thing I would probably do then is find my most recent backup, tape or whatever, of D and recover it completely. Okay. Might have lost some data due to elapsed time between the last backup and whenever the disk died. Okay. But pretty reasonable fault tolerance for a system of that era. Okay. But the other thing this illustrates is that you can sort of combine these concepts of being able to take a single physical disk and breaking it up into partitions with doing various things across the disks with the partitions, mirroring in this case, okay, and striping in this case. All right, so let's come back for a minute to the current computer. This is a modern workstation. I think this thing's about a year old. Okay, it was a reasonably high-end PC when it was purchased. Okay, and sitting on here is at least what Windows thinks is one disk drive. Okay, as opposed to, sorry, let's go back to the other display. Okay, on this one, okay, this computer management is an operating system utility. The operating system here is seeing two physical disk drives. The operating system knows that C is mirrored across these two, and it's the operating system that's responsible for doing the mirroring. So every time I write data to C, the operating system, or to C on disk 0, the operating system is basically duplicating that write operation to the mirror partition on disk 1. Likewise, every time I read data, say from disk drive D, the operating system knows, well, that's split across two D partitions, one on each disk, and it's going to split the read operations accordingly, depending on what data is stored where on which two disks. The key issue here is that it's the operating system that is managing this process. And since both this mirroring and striping are actually versions of RAID, this is an example of what's known as software RAID, because the operating system, which is software, is what's responsible for doing all the things associated with RAID. So now let's come back to this particular computer. This computer, on the other hand, is seeing one disk. Clearly, by only seeing one hard disk drive, the operating system itself can't be really concerned with anything associated with RAID, because any form of RAID would require at least two disks. So the operating system is just basically out of the equation here. Okay, the operating system thinks this is one single disk, and it's treating it as such, one single physical disk. But in reality, this is not one single physical disk. And let's see where you can find that information. Well, first thing I'm going to do is come back up here to Computer and choose Properties. And then I'll do something we did earlier in the semester for another purpose. I'm going to open up the Device Manager. Okay, and now I can get rid of that Properties page. So here's the Device Manager. Okay, and let's see. Let's switch the view to Devices by Connection, which we're familiar with. Okay. And if I come down here, okay, so there's the computer, there's the ACPI client, there's the PCI bus root, to the main chipset that's attached on the motherboard to the CPU and memory. And if I come down just a few items here, here's one, Intel ICH8R, ICH9R SATA RAID controller. Okay. There's a chip on this motherboard manufactured by Intel which contains in hardware all of the smarts needed to be a RAID disk controller under the SATA standard. Okay. And if I expand this, I'll see three things under here. I'll see, well, I've got a DVD drive attached to it, I've got a CD drive attached to it, and I've got something called an array. Okay. Now note, there's no little thing here to expand the array. I can't see what the array consists of. Why? Well, once again, this device manager is an operating system utility. The device manager knows that this SATA RAID controller is attached. It knows that there's a storage device being connected, or multiple storage devices connected to that RAID controller, but it doesn't understand any of the details of it. So whether this array consists of 2 disks or 12 disks or 200 disks, whether it's RAID 0, 1, 2, 5, 6, 10, whatever, the operating system hasn't a clue. Okay, why? Because this is an example of hardware RAID. There is a hardware device, in this case the disk controller, which is in this case just a chip that's embedded on the motherboard of the computer, that's doing all the RAID specific functioning and hiding all that rather ugly detail from the operating system, which sees simply disk 0 as if it were one physical hard drive. Okay. So, no software RAID here, hardware RAID. Okay. So how do we see the specifics of what's inside this array? Well, we can't do it from the operating system itself, but we can do it from an Intel utility that I have installed as a program under this operating system. And let's see, I already opened that program up, so let me just bring it up here. This is the Intel Matrix Storage Console. Okay. And let's see, let me see if I can get all this on one screen here. Okay, and it's showing me my RAID controller. Okay, it is showing me, well, there's the RAID controller, and it's showing me the CD and DVD drives. So there's port 2 and port 3. There's the CD-ROM, which is shown here, and there's the DVD drive, which is shown here. Okay, and it's showing me quote-unquote arrays, but if I look, I'll see there's only one array. Okay, array 000. Okay, has a series of hard drives attached to it, 2 of them, and they're both WD1600HLFSs, 75G6UO. It's not always required that hard physical disks in a RAID device be exactly the same make model, but it helps simplify things. Okay, so in this machine, I actually have 2 hard disks that are identical. Okay. And if I look here, let's see, what are they? They're generation 2, so they're second generation serial ATA devices. I believe that means they're 300 megabytes per second maximum. There's the model number, there's the serial number, there's the firmware on the disk. Okay, they're 149 gigabytes each. They use 512 byte sector sizes. Okay, and they're members of this single array. Okay. If I go look at the details of the array, I will see that the array has 2 hard drives, 512 sector size. Okay, its total size is 298. Okay, and that its RAID level is RAID 0, which is striping. Okay, once again, fairly typical of a higher end, although not necessarily quote-unquote high-end workstation, particularly pre-solid-state drives, as this one is. Okay. Basically, I've striped the data across 2 hard drives here just in order to speed things up. So roughly the disk I/O on this particular machine goes about twice as fast as it would as if I didn't have RAID 0. Okay. But once again, the fact that I have RAID 0, the fact that that array consists of 2 drives as opposed to 10 or 20, and that's all invisible to the operating system. All the operating system sees is this one disk 0, which it thinks is just a basic disk, just a single hard drive. So that's a couple of different examples you've seen. Now let's step forward and look at something a little more akin to a modern server setup. Okay, although in this case the hardware I have available to me is kind of old, so I wouldn't call it absolutely current, but it's not the dark ages. And for that I'm going to bring up a remote console here. I'm logged on to Tecolote. Okay, and Tecolote is my own personal file server basically. It's an old cast-off rack mount server with an attached drive array. So it's actually two pieces of rack hardware sitting in a rack and hardwired to one another. Okay. Looking at, well, here's the device manager. Okay. And under the PCI bus, I see two attached Dell PERC RAID controllers. There's the first one, and there's the second one. Okay. The first one, well, both of them have RAID devices attached to them, okay? But frankly, the more interesting one is this Dell PERC 5E, which is a later generation of PERC device, okay? And just to show you once again what the operating system sees here, let's come back to storage. Let's see, disk management. And let's see what the operating system thinks is attached to this server. Okay, the operating system is seeing two hard disks. Okay, disk 0 and disk 1. Disk 0 is roughly 3.3 terabytes. Disk 1 is 136 gigabytes. Disk 1 has two partitions on it, a reserved diagnostics partition that's Dell specific in this case, and a boot partition with an operating system that's 136 gigabytes in size. There's a USB expansion drive that's attached to this machine. It's actually used for backups, and it's about 0.9 terabytes. And there's also a DVD drive in this system. Okay, so the operating system here, in terms of hard drives, thinks there's three of them. This USB drive, which is disk 2, this relatively small hard drive, which is the boot drive, and this much larger disk 0, which is where all the data is stored. Now note the name here, SAS Array, but that's something I, as the system administrator, typed in. Okay, the operating system does not really know this is an array and did not automatically create that name. Okay. Note once again, three volumes managed independently. The C volume for the boot, the B for the removable drive, and then the array is volume S. Okay. So, back here. So how do we see the details of this? Well, once again, I need a hardware vendor specific utility, because what's happening is these Dell PERC RAID controllers are implementing RAID in a hardware sense and therefore hiding the details of the underlying disk drives and organization to the operating system. In this case, there's actually an application that runs within a web browser that shows me this information, and I've just opened it up for you here. Okay, this is the Dell Open Managed Server Administrator. Okay. And I can see the computer, the actual hardware I'm running this on is a PowerEdge 1850, which at this point is probably about a 5-year-old, 6-year-old machine, something like that. Okay. Here are the two controllers, the PERC 4E SI and the PERC 5E. Okay. And we're looking at the details of the PERC 4E. Whoops, it logged me out. Hang on. Okay, pardon the delay. I had to restart the application. I'm not quite sure why. I guess it had timed out from when I started it earlier. Okay, so back to storage here. So if we look at storage here, we see there are two hardware RAID controllers in here. I'm going to open up the details of the first one. I see there's a battery, there's a connector, there's virtual disks. If I click on this virtual disk, I see that connected to this controller is one virtual disk of size 136.62 gigabytes. Okay. It is a RAID 1 disk, meaning it is mirrored. And to see what's being mirrored, if I come up here to connector and click the plus, and then continue down here and look at the physical disks, I see that what I have are two physical disk drives. Let's look at the details of the first one. Okay. I have two physical disk drives. They are SCSI disks. Okay. Hard disk drives. Okay. They're 136.62 gigabytes in size. Okay. They're manufactured by Seagate, and there's their model numbers and their serial numbers. Okay, and both of these are identical. See if they have consecutive serial numbers. Let's see, 3KS5A, not quite consecutive, but probably came off the line the same day. Okay, and those two disks are organized into a mirrored RAID array that shows up as one virtual disk, which is in turn what the operating system sees. Actually, I don't have that mirror open, but it sees that as the C drive. Okay, that's my boot drive. And this is pretty typical for a server. Typically, servers have mirrored disks that they use for boot drives. Okay, and that why? So if one fails, they can, well, first off, if one fails, the system will continue to run. Doesn't even need to be rebooted at right that moment. Okay, I can later on at a more convenient time take the system down, take out the bad disk, put in a good disk, or actually in most modern servers, I can actually do what's called hot swapping. I don't even need to shut down the server in order to do that. I just go to the server, open up the front panel, pull out literally the disk that's bad. It'll usually have a little red flashing light to it, shove in a fresh one. And in this case, the firmware embedded in this PERC4E SI controller will automatically detect the change in the disk. It'll scan the new one to see, ensure it's compatible with the old one. If it is, it will immediately start initializing it as a copy of the other disk, and to maintain the RAID mirroring. And it will do that entirely in the background without any knowledge of the underlying operating system. All right, so that's the mirrored boot disk. Fairly standard fare in rack mount servers today. Let's go look at this other controller. This is a PERC5E. Okay, and if I look at its virtual disk, I'm going to see SAS array there. This is a RAID 5 disk of roughly 3.3 terabytes. Okay, known as Windows Disk 0. Okay, so this is that. Is this that S drive we were looking at earlier? Yes, I think it was. So, what's in here? Well, let's open up the connector, open up the enclosure, go to the physical disks, and now you'll see why I have this displayed in full screen, because there are 1, 2, 3, 4, well, let's see, 0 through 14. There are 15 disks in this array. Okay? Literally in rack mount terms, I should have taken a picture so I could show it to you right now, but there's there's a 2 rack space server that is this PowerEdge 1850. Actually, it's a 1 rack server, and sitting under it is about a 4 rack space array, and these disk drives just plug into the front of it. And there's room for 15 of them. Okay, so there's just 15 disks lined up on edge right across the front of that. Okay, and that enclosure is attached via a cable to this PERC5E adapter, which is sitting in the rack mount server. So let's look at the details of one of these disks. Okay, first off, I see these are SAS disks, serial attached SCSI. Okay, a slightly newer generation than the boot disks were. They are, in fact, hard disk drives. They are all 278.88 gigabytes, almost 300 gigabytes apiece. Okay. And let's see, what are these? These are, vendor ID is Dell, but I'm sure they purchased them from somebody else. I just don't know who. These disks are actually fairly old, 7/28/2005. So you remember how earlier in the semester we talked about, storage or disk drives being used for a lot of years in enterprise scenarios. Well, here's a nearly 12-year-old disk drive still being used. Okay, I'm sorry, not 12-year, a nearly 7-year-old disk drive still in use. And if I were to open up all of these other ones, I would see that physically they're all the same. They're all 300 gigabytes plus or minus. Well, 300 times 14 would yield roughly a 4.2 gigabyte disk, and yet I don't have 4.2 gigabytes of available storage. This virtual disk is in fact, 3.3 something, 3.346 gigabytes. So where'd the extra space go? Well, I know in RAID 5 that one of these disks, or at least one disk worth of data, is all parity data. Okay, so effectively my 14 disks are really only 13 from the point of view of storage. But 13 times 300 is 3.9, not 3.3. Where did the other two go? Where did the other 2 disks worth of data go, almost 600 gigabytes worth. Well, if I look down here in the state, I'll see why, or at least see a hint of why. You notice that the first 13 are all labeled online. They're actively being used. Okay. The last 2 are labeled ready. Let's open up one of those and see what the difference is. And the difference can be traced right down here to this line that says hot spare dedicated. Okay. These are what are known as hot spares. Actually, this one and the next one are both what are known as hot spares. They are sitting in there. They have power running to them. Okay. The not the operating system. The PERC 5e controller knows that they're there, but they're just ready reserves. They're just standing around waiting for one of these other hard drives to die. Okay. And when one of these hard drives dies, the PERC 5e controller will automatically detect that. It will, quote unquote, cut off the dead drive, say it's number 12 here. Okay. It will bring either 13 or 14 online, and it will immediately start to rebuild the contents of what used to be on 12 onto 13 by doing all the appropriate parity math based on the contents of these other 12 disks. Okay. Once again, because this is hardware RAID, it'll do that all in the background, all without knowledge of the underlying operating system. So what I have here is in fact 2 layers of fault tolerance. Okay. Layer number 1 is the fact that the 12 disk array is RAID 5, and therefore any one of these 12 disks can die without losing any data. And then in addition, I have these 2 disks set aside as ready reserves, such that if any of the first 12 die, one of the 2 reserves will immediately be brought online and will be immediately reconfigured as a replacement for the failed drive. So I could, in theory, lose 3 drives in this array, not all at the same time, but say spread across, a month or so. 3 of these disks could die, and I would still have a functioning array and would never need to reboot the operating system. Okay, so this is the most complex example of SCSI that we're going to look at, and that'll do it for this video.